Hi everybody, welcome back to this new WeeW episode for the STM32F1 tutorial, and finally we are starting the I2C communication. So we are going to start with a short introduction, as there is a lot of material on the internet and YouTube about the I2C communication, but we are going to spend most of our time to have a practical example and make the setup on the STM32F1. Finally, we will visualize the signals using a logic analyzer, and we will have some remark and caution about the I2C communication. Before jumping to the video, let me take the moment and thank everyone for their support. I will keep doing my best to provide this quality content. So as usual, to support the channel, you can give us a thumbs up, make a comment, or subscribe and stay tuned. As usual, the code that we are going to write within this episode is available on GitHub. You can find the link in the description below. We are going to use only C language, and the program for programming, debugging and loading in the STM32F1 is a KL version 5. And finally, the level that you do have here is a beginner level, so there is no complicated C, and we are going to use two libraries, which is the GP library and the SysTick library that we have produced in the previous tutorials. You can find the link in the description below also. Okay, the hardware that we are going to use is the STM32F1 aka Blue Pill, also a logic analyzer, and finally an I2C device. So I put it here as an I2C device because you can really use whatever the I2C device that you do have. So, and the address that we are going to use for this I2C device is the hexadecimal number 78. Okay, so within this tutorial we are going to start with introducing the I2C communication, and then we are going directly to start setuping the I2C init, and in the STM32F1 of course we will going to use the datasheet and the reference manual to guide ourselves and to build the function. Then we will make a setup for the I2C write function to have a real example. Then we will debug and review the signal output using the logic analyzer. Finally, I would like to share with you some important caution about the code that we are going to write and general about the I2C communication. Good, so let's jump to introducing the I2C communication. So first of all, the I2C communication, so the I2C is sometimes written IIC, and this is short for inter-integrated circuit. Also sometimes you can find that is called TWI, which is a two-wire interface, and this is a half duplex, means that it uses only one wire for the communication. So the communication is established using two wires, the SDA and the clock wire. So the signal wire is SDA and the clock is the signal clock wire. So, and also the communication speed is 100 kilobyte for the standard mode, 400 for the fast mode. But recently there is a new communication which goes from 1 megabyte to 5 megabyte, but this is still not really used a lot. So most of the time for the IC that you find in the market, 100 and 400 kilobyte are the common ones. So let's see how the circuit are built. So we will have the master microcontroller having the SDA and the SCL, where SDA is for serial data line and SCL is for the serial clock line. And usually there is a pull-up resistor that's added, and this is to clean the signals. If you would like to look for it, you can just type it in the internet, but this is just removing any noise happening when you go low, so that's you go high, sorry, when you go high. So this is what you used for. And after that, you connect devices to the wire for the SDA and SCL. And as you can see, each one of the device will have a specific address. And the communication will go by signaling this. And based on that, normally you can add up to 127. But in reality, it's not possible to do more than 30. Because there's more noises and there's some parasite signals, so normally you can go to up to 30, but it's already something really good. Okay, so now we introduced a bit the I2C. Let's take a look more about how the communication works. So let's go back to this initial circuit, and when the microcontroller will start, it will have to initiate a start condition. This is not an I2C init, but there's a start condition for all the devices, so they will understand that the microcontroller is starting a new communication. Then the microcontroller will send a 7-bit address, and this 7-bit address will be read by all the devices, plus another bit which will be a read or write, which means that we are sending an address and we are saying after that we are reading or writing from the device. And finally, the other devices or the slave devices will send back an acknowledge bit or not acknowledge. So if there is no acknowledge, there will not be anything, but an acknowledge one means that the device has understood that there is a signal. And this is to establish the communication with slave and will initiate or activate the slave that we are going to select. After that, after the activation of the slave or the establishing the communication, then there is a 8-bit signal sent with each time an acknowledge bit. And this one is also preceded by a number of 8 data bits with acknowledge each time. So there is a number that like for the communication. And this is the part where there's a sending data and instruction to the slave device. Actually, it's a sending or receiving depending on the read or write bit. Finally, to close the communication, there is stop condition. And this stop condition also is initiated by the microcontroller. And all the part in between is called the transaction between the device. So this is in general how the communication happen between the microcontroller and the devices connected to the SDA and SCL lines. Just for a caution, the other devices are powered separately. So the SDA and the SCL line are not powering the devices. Okay, so now that we had a short introduction to the I2C communication, we can jump and start our init function. Okay, so we are starting from almost a blank project. So already adding the library for the drive and the sysdig, and added 2 files, the C and header file for the I2C. So these ones are blank. Let me close this one as we don't need it. And let's first start by taking a look to the datasheet and the reference manual to locate ourselves. So starting with the datasheet, let's go and check the I2C is connected to which bus. So let's go to the block diagram, and if we locate here, we do have the I2C1 and I2C2. Both of them are in the APB1, so we have to go and activate them here. After that, let's take a look to confirm which pins are connected for the I2C. So if we go to the pin connection, no I2C here, no I2C here neither. Yeah, we do have. So the I2C2, this one, I2C clock is not this one. Actually, this one, yeah, sorry. So I2C2 is a PB0 and I2C SDA is PB11. So PB10 for I2C2 clock and PB11 for I2C2 SDA. So this is the I2C, the peripheral number 2. And if we continue, and we take a look, so we don't have I2C here. We go, yeah, and this is quite clear here. So we do have the I2C1, so the peripheral number 1 is connected to PB6, and I2C1 for data is connected to PB7. Perfect. So as if we can summarize, so I2C2 is connected to PB10 and PB11, where I2C1 is connected to PB6 and PB7. Perfect. So we can jump now to the reference manual and see how we can activate them. As we said, both I2C peripherals are connected to APB1, so we go as usual to RCC, the register page, and APB1 enable, and they are for the enable I2C1 is bit number 21, where I2C2 is bit number 22. So just before we move on, as usual for the STM32F1, if we would like to use any peripheral, we have to go to APB2 enable here and enable alternative function. So this is whatever the peripheral that we are going to use, we have always to activate this one first. So let's jump to our code and start. So it's a void and I2C init, and we can put here the let's start by a char here, and we put the here we call it I2C, so we will select the I2C a number later on. Okay, so here we will start by putting, first of all, as we said, we have to put RCC APB to enable and or equal, and this one will be equal to 1, which means we are going to enable the alternative functions, the one that we have seen previously. Then if we put here I2C, so if it's equal to 1, let's start. So if I2C is equal to 1, let's go back again to the here. So we said APB enable, so pin 21 means it's 1 2 3 4 means it's a 2 hexadecimal. Okay, let's go here. So this one will be equal to RCC APB1 enable and plus, or, and it will be 0 2 and then 0 and 1 2 3 4 0. Okay, so this is, here we have enabled the I2C2. Okay, and after that, now is we have to enable like this. So here we have to pin enable. So we already added, just let me remove this one. So we already added here JP drive library, so it's very easy to start making it. And for the I2C library, it's quite a new thing that we are going to use. So the pin will be, so let's say for the one we said PB, so PB, so for the both of them like PB6, and for both of them it will be an output. Let's put it as fast as possible, but it's yeah, an output at 50, but both of them are alternative functions open drain. So alternative function open drain, and this is because both like the data one will be both sides, so we have to put the open drain so we can use the pull-up register later on. Okay, so we said both 6 and 7, we just have to copy this one then and put here the pin number 7. Okay, so this is, we enabled the pins. So now we can jump on taking a look how to set up the I2C peripheral itself. So let's go back again to the reference manual, and we close this one. We have to jump to the I2C, and we go to the registers. So the first step in the register, and the most important one, is to restart or reset the I2C. So we have to go to the control register and start by resetting it. So let's take a look quickly, and let's put, so I2C, so for this one is I2C1 and control register, and that will be equal, so the reset we can put like, we even put or equal, both are same, and it's a hexadecimal number of 00 like this. Okay, and after that, so when we put it here, we have to force it again. So just in case, to remove the reset, so we have here to remove the reset, so we just put this one, and no, sorry, it's the opposite. So here and we have to take all, remove the reset. So now we reset it and we removed the reset status. So after that, so there's a little bit of setup, but let's go quickly on it. So after that, there is here for the CR2, here there is a setup of the frequency. So normally, even so for our example, even putting 0 is fine, but for this frequency this time, so the setup of the control register, I'm going to put 8. The detail are not really important for the setup for this example itself, but if you put 8, it should be fine. So for the CR2, for the frequency here, you will put 8. Go here, I2C1, and for the CR2, just equal hexadecimal, 0x8. Okay, but now after this one, the most important step, which is the setup of the speed of the I2C. So let's take a look on this one, and we will really take more time on this one. So this is the setup for the CCR and how to take the setup here. So just to give you one background, so I will use the STM cube here to show you what's happening with the microcontroller from clock speed perspective. So the input to the whole peripheral, as you can see in our configuration, is 72 megahertz. So the input to the whole peripherals, and then we go to PB1, and from PB1 there's a division here. We don't know, because if it was by 1, that will not be accepted and it will maybe destroy your microcontroller. So it's 2 here, minimum as a 2, and this is the APB1 peripheral clock. This is the minimum, the maximum speed of the clock as an input to the peripherals for APB1. So as we do have here 36 megahertz, but we need to check what the Kale in the startup program has set up for this one. And to check for this one, we need to find the register for this point. And if you go here, sorry, this is a little bit complicated, but it's quite interesting to know. So if you go to RCC again, and you go to the register, and if you go to configuration 2 for this register, and the register is, if I go back, actually it's not configuration 2, so let me check again. Not this one, CFR. Yeah, I think it's configuration 2. Yeah, it's not that one, it's block configuration. Not really. Yeah, that input. This one. APB, no, this is the APB low. Yeah, this is the one. Not, it's configuration, not configuration 2. And we need to check in our Kale startup program which one has been selected. So if we go back here and we check, so not here, actually we need to go to the Kale, and before to check how it was, one of the update, you can go to debug, use simulator. Please use the same configuration as shown in the first tutorials, like this one. And after that, if you click on this one, we will go in simulator mode and can check. If we go to RCC and run and check configuration. So if we go, let's make it bigger to see how the configuration has been made for this one. And if we go, we set which register for the register, and this is the APB1. Let's take a look. Where is the APB1? Not really. Okay, let's check again. And this is the configuration register. Okay. And where is it? Ah, yeah, this is the one. Okay, it has been set to 4, so means that it will be, so 4 is this one. We have the input as 36 megahertz. Just in case, always checking this parameter is very important to be sure about it. Okay, so let's open back again and close. Good. So let's go back here. So we need to divide the number that we have, 32 megahertz, by a certain number so we can get our code correctly. So what we need to do, so let's create 2 variables that we provide here as a define. Okay, define, and we call I2C, and let's call this one fast mode, and it will be 0x2D. And the other one, let's just copy here like this, and we put I2C standard mode, not fast mode, and we put this one as the P4. And this one, based on this one, we can set up our speed for the I2C. let's go back here, and we can create the function we add here, and we add the we put it as a char, and we call it, let's put it as unsigned short is better, unsigned short, and we put it speed mode, okay, just in case. Okay, and then what we can put, so the I2C1 and the register, as we said, CCR will be equal to the speed mode. Okay, and the last thing to do before we activate the register, if we go back to CCR, there is a configuration for this one. This is quite very complicated, but you can take a look on it on the internet. But they are saying here for this one, you can put, as you are at 100 megahertz or 400, you just put around 8 to 9, and that should be fine, as here. Okay, so if I go for the last one, I2C1, and for this one, it will be equal to the 9 hexadecimal. Okay, so we finished almost everything here. Okay, let's make it clean and nice. Okay, and what we can put like this. And the last thing is to enable the register. We go here and we go to, again, control register, and this is the PE, which is peripheral enable. If we go here, and that's all. So let's enable the register. So we go I2C1 control 1, and we just put the enable register. Actually, it's the opposite. 0 or even 1 is fine. Okay, here we finished with the I2C1. Let's just copy everything and put else like this, and else if it is equal to 2. So this one is the next one, then it becomes 4, and that's good because I have to put this one, else it will be totally wrong. Yep, let's, like this is correct, so I don't have to worry. Like this, so we have 4 zeros and perfect. Okay, and after that, so here we said that this is PB10 and this is then PB11. Okay, and for all the rest, just changing to 2 here. And we do have our init function ready. We just have to copy it here. Okay, let's take a look. Okay, so let's copy this one here and put the init function at here. So we would like, let's try to activate the I2C2, and we would like to have the I2C fast mode. Okay, so let's save and build. Okay, no error, no warning, perfect. Okay, so we finish this function. So now that we finished the initialization function, we can go and jump to start our I2C write function. Okay, let's start back from the initial screen we left in the previous part, and we are going to jump directly to the I2C drive section, where we are going to create the I2C write function. However, this time what we are going to do is to create micro function, the start step, sending the address, sending the data, and finally the stop step. And we are using this as a modules in our I2C write function, and this modularity will help us to create other functions later on. So what we are going to do is to create the first start step, and as usual, so we will need to have the I2C 1 or 2, so we call it I2C start. Yeah, and we put exactly same as the init function. Let me close this one. So a char called I2C. Okay, so let's do this. Close here. And normally, so if I2C is equal to 1, let's start writing based on that. So now to understand how to set up the steps in the STM32F1, let's take a look to the reference manual. So let's go quickly to maybe function description, yes. And when you see here, not a slave transmitter, we would like our microcontroller to behave as a master transmitter. Yeah, perfect. This is what we need here. So this is the sequence of how the master is going to work. And we are going to use only the 7-bit address. The 10-bit address is really not used at all. So there's only a few examples and we don't need to go through this one. So the first step is to set the start bit, and we will show yes when, and this is, so this start bit is cleared, so we have to read the to first set up the start bit, and then we have to wait and to see until the SP, which is in the status register 1, is cleared. So let's go and check. So first of all, we need to set this start bit here, which is a bit number 8 or the hexadecimal 100, and after that we have to wait until which one? So this one, which is the bit number 1, the start bit, is getting to 0. So what we need to do, first we set up the start bit, and then we wait until it becomes 0. So let's go to it. So it's quite straightforward. So I2C 1 and control a register or equal the 100 hexadecimal, and this is to set the start bit ready. And after that we have to wait. Okay, so while, and let's put this one like this, not opposite. So while, and it's not, so I2C, and yes, I2C, actually it's I2C 1, and the status register 1 and 1. Okay, we have to wait for this one until it finish. Okay, so this is quite very simple and straightforward. Let's make it a little bit bigger. So first of all, we set up the start bit, and this will start the start function from signal perspective. Then we will wait until this bit is getting equal to 0. So if it's equal to 1, we still know. Okay, so what we will do here, then we put else, and let's put if again, and again if it's equal to 2, everything else will be equal to 2 here. And that's all. This is our start function, which is, we can also start building it here. So let's put, oh okay, so void and I2C write. Okay, and as usual I2C, let's copy it from here. Okay, I2C, and what we can add here is this function I2C start using I2C. So this is first step that we are going to use, and here we are. Okay, so that's the first part of it. And then now we have to go to sending the address, and this is a little bit more complicated. So let's go back to this one. That's almost the most complicated step. So let's go back here, page think not this one. Let's go back. Master transmitter, perfect. So then we have to send the address. So by sending the address, first of all, we have to send the address here. And so after we get this one, so when we are, we have to wait this one. This A means we need to wait for some acknowledge. And after we get the acknowledge, we have to clear the address 1. And this is cleared by reading the whole status register 1 and status register 2 in sequence. So it's a little bit complicated, but so first of all, sending the address, waiting for the acknowledge, and after that we have to keep reading and reading the address again and again. Sorry, the status register 1 and 2. You have to follow this one, else this one will be sitting in this step. Okay, so let's start doing this again. So void, and we will put it I2C address, call it add, and as usual, so we need to put the I2C part. No, that's wrong. So the char I2C, but also we need to add another char that we will call the address. Okay, so as usual here, let's go and put if I2C is equal to 1. Okay, so if I2C is equal to 1, let's try to make it quickly. So first of all, we have to send the address, and sending the address, so this is page 760. Okay, so to send the address, we have to go to the data register, and we just write equal to the data register. Even before, so as I said, we have to read as data register 1 and 2. So let's create a variable, a volatile integer, or even char. Let's put an integer just in case, and we call it temp, and this is the one that we are going to use to read the status register. So what we are going to do first is we put I2C1 and data register here, and that will be equal to the address. Okay, then what we need to do is to wait until the acknowledge is received. So if I go to here, this one, and the address acknowledge is this one, so we have to wait until that one is equal to 0. Okay, so let's read it first, is better. If we go here and this one, okay, so this one, if we go, not this one too, just a moment. Yeah, address. So we need to wait. So if it's equal to 1, means address is mismatched. So this is what we need to confirm. But so, sorry, if equal to 1, the address is matched. So let's take a look and write it. So let's put while. Okay, and let's put, so I2C 1, yes, and this one I2C, sorry, insert, so I2C SR1 and 2. So just first of all, we need to confirm if it's equal to 0, just in case. Okay, let's add another one here to avoid any mismatch. And after that, just only after that, we start opening a loop. Let's copy just in case here, and starting, so I can remove this one and remove the 0. Okay, and here where this is a tricky, and this is how it works. So we have to put temp is equal to I2C. So just to explain to you, so why I'm putting here equal to 0 when it is equal to 1 is very important. So we need to wait. That's why equal to 0 here. We need to wait until it is equal to 1. And when it's equal to 1, we need to keep looping until it is equal to 0. Else, the microcontroller will be much faster than the peripheral and the signal will not be sent properly. Okay, so I2C 1, this one is status register 1. Okay, and we add here, we keep reading them to until, so if we do have, just in case, the I2C 1 and here status registers, so I go to SR1, this one, so until it's equal to 0 again. So if it is equal to 0 again, so let me put it here, okay, then we can break. Okay, so we keep trying to read, and if it's equal to 0, we immediately break. And I think we are good. So that's the point here. It's very important that, yeah, there's another thing that I totally forgot about. So we do have the address, but by sending the address, we do need to add the read or write. So char, we call it read write, this one here, because here when I send the address, the first digit, or the first bit, sorry, the first bit that is sent, or the less significant bit is which is sent, will say if it's a read or write function. So I will put here, it will be or the read write. Read write will be 1 or 0. Okay, then that's all. That's what we need. So let's copy everything and we put else, and after else we paste this one. So if it's equal to 2, we can change everything here to 2. 2, careful to not change the one that we should not be changed. That's a mistake I do a lot. Okay, perfect. So based on that, I need to add this to 1 here. And so actually not both, because I have to put like this one, because this is a write function, and in the write function I just need to put it as 0. Okay, where a reading is 1. So I2C address is address, that's what we will do later, and this one will be equal to 0. Okay, that's good. So we still have the 2 last steps. So you see how write function is built and quite simple to do. So the next step is about the sending the data. So let's go back here. So page 760. So as you can see, let's make it bigger so we can read it. So after we had the acknowledge of the address, we can, and we finish the EV6 where we already had the address bit cleared. We can check for the start sending the data. So what we need to do, we have to wait until this register, the TX1, is empty, and that's very important, so we can send. So first of all, we have to wait until it is empty, and then so we use this one, and after that we can send the data. So it's a 2-step. So where is the EV? Yeah, 1. So it's empty and we wait, and the EV2, so we can put EF is equal to 1. So when it's equal to 1 means it's sending, so we have to wait again, that is it's 0 again. Okay, and after that, so we can choose one of them to TX1 or BF1, both are fine to use this one. So let's jump to our code. So for the TX1, if we go to the status register, is the bit number 7 or the hexadecimal number 80. Okay, let's jump back here and let's create. So we go void, and this is, we call I2C, let's put data, we call it data. And as usual, so we need to add the char, the I2C here, and another char, not I2C, but we call it data. Okay, so for this one, it's quite so as usual, let's add the if one, so if it's I2C 2. Okay, so if we do have this one, so first of all we need to confirm that the bit not this one, bit number 7 of TXE is equal to 0, so we can send. So what we can do, so while, and this is extremely important step, so I2C 1 status register 1, and the hexadecimal 80 is equal to 0, means we can go ahead. Okay, so if this is fine, we are good to go. And after that, I2C, sorry, let's put, so I2C 1 data register is equal to data. As simple as it is. But we need to stay there until it come back. So until, so as, because when it's sending, still we have to keep waiting, and that's very important. And that's all. This is the step, and this is very important to respect these kind of steps. Okay, so let's put the else, put like this, and put equal to 2. Let's change this one to 2 and 2. Perfect. So let's add the data here to this one, and let's copy this function. Okay, so you see now we still have kind of modularity to our function and become very simple to manage it. Okay, so this is a data, we get it here, and actually, yeah, that's correct. But actually the idea, instead of putting this, let's put it like this, and we put this one here, and instead of, we can have an int I, okay, and we put it equal 0, and what we can do, while data of I, okay, let's make like this. So if we have a lot of data to send, it will keep sending again and again. So we put I here, and we don't forget the I++, or we will have an infinite loop. Okay, perfect. So now we can send as much data as we need and as we want to. And we still, the last step is the last function, so void. And we call it I2C stop. And here we just need only the I2C, like this. So actually it's almost like that, almost. Let's copy this one, so it will be this. Ah, that's wrong. That's totally wrong. And let's put only this one here. Okay, so if I2C is equal to 1, now as we are at our latest step, what we need to do is, just in case, so we have to create another volatile. So let's go back here, 70, here the 760, and to stop the function, we need, so which is here the EV, so this is the stop, which is equal to P. Before the P, the EV82 here is to check either TXE is equal to 1 or BFE is equal to 1, and then clear by reading this one, SR1. So what we are going to do is, just in case, because this error happened many times, we are going to read the status register 1 and 2, just in case. So what we are going to put here, so to the stop function, we are going to need a temporary volatile, just in case. We are going to add it to the stop function here. So what we are going to read, so we can just copy the from here. Yeah, let's copy this one. So we read this one from the stop function, so we put this one equal here, and we just put the stop in the control register. For the control register, the stop is the bit number 9. So what we will have to put, let's take this one, and actually I need to put this one as 1, and instead of 1 it will equal to 2, and that's all. That's what we need. We just have to copy this one again, paste it here, and let's change every 1 to 2 carefully. Okay, and here we are. So we do have our stop function ready. We can just go here and putting the I2C. Okay, it's a little bit heavy, but it's very important to go through the step, and I wanted to show you from where this code is coming from. So let's make this one smaller, so we have some visibility on how this function is working. So we created first the function that start, and then the function that send the address that we need to use, and after that we go to send some data before stopping everything. And we don't have here any if condition, as everything is embedded within these functions, so the maintainability is higher and easier to do. So let's add this function to the header. Let's go here, add to the header, and we are ready to use this function. Okay, so let's put it here. So we activated the number 2, and for the address, as we said, is the 70, I think 76. Oh, sorry. So the address here is the hexadecimal 76. We'll check later on, and the data we can send. Let's put here data. What we call so a char, and we call it data, and we put let's put only 2 for the moment, and we call them, let's put 0x00 and 0x02, for example. Okay, let's put this one here and put this, remove this one, and remove the brackets here. Okay, yeah, and I forgot that one. So let's save and build just to check if there's any problem. Okay, there is something. Yeah, end of line, of course. Let's put here, and another end of line that we need, let's put here, and let's save again, build. Okay, 0 error, 0 warning. So that's perfect. We are ready now to have our test. So see you to the next section. So we just finished writing a modular write function. We can jump and see in the signal and make some debug, if any. Okay, we are reaching the most excited time. So when we're trying to see if the code is working or not, and we try to debug if something happens. So let me first start by correcting this. As I was expecting, it was 78, not 76 hexadecimal. And we can, let's save again, build and load. So before running the logic analyzer, let me show you a little bit the circuit. So we do have here our STM32F1. This is the logic analyzer, and it's connected to both the SDA and SCL lines, and the two amber or orange lines here are connected to the IC device that I described it to you. I'm not showing for the moment because you can take any other device and that should be work same. Okay, so let's open the logic analyzer. Before that, I think better let's add some delay, small delay of 10 milliseconds just in case. Okay, so let's save, run, build, and let's take a look. So let's go to the logic analyzer and run it. So you do have here, this is SDA and this is the clock channel. So if we go here, and this is good, but there's something missing. So you can see that there is a setup, right? So there's the we have the address, which is a 78 plus the acknowledge, if you can see here in blue. So I'm trying to, yeah, this is the blue one that you do have here, but I'm not seeing the data I'm sending, and I'm suspecting, yeah, my code, there's a mistake. Actually, you see here in data, so while data of I, and if this is already equal to 0, it will skip it. So I will put here 1. Let's try and build again. So let's go to the logic analyzer, run it, and here we are. So we do have first our address plus acknowledgement, and then we do have 2 steps of data. Let's zoom in one of the data and take a look at it more carefully. So we can see that the data is sent, and if I zoom further, you can see that my duty cycle is 400 kilohertz, and this is what we wanted to have. So let's try and change from the fast mode to the standard mode. Save, build, run, and let's take a look. If we run again, we do have our data. Let's zoom a little bit here, and you can see that we are at 100 kilohertz. So our setup is quite right and very good. Perfect. So we are able now to send the signal with the frequency that we need. So we are quite having a functional program that can send I2C signals. Perfect. So now I think we have seen everything, but I would like to add some caution in the next section. So we finished our debug and review signals. So we have been quite conclusive without too many issues. So now I would like to get with you to this caution that I found out when start planning and programming this I2C. So let's take a look together. So guys, let's go back to the function that we have written together. And I wanted to put it modular, as there's sometimes something very important that we can create, and most important is about the sending the address. So within our code, when we start sending the address, if we go to the address function, we created a function that only take in consideration if the address is sent. So we have to be very careful at the time about how to create it. One of the solution is, instead of putting a void and giving no output, you can put here as an int the address output. It will be 0 or 1, and you put an output as a 0 if there is no address match or there is a non-acknowledged signal, and as an output you put a 0 here. And then in your modular function, if the address is not acknowledged, you don't send the data and you return a 0. So this is a very important step, because without this one, if you want to have a more efficient program, this one will not be working. Another one that I would like to share with you was about sending the data. So this can looks a little bit verbose or having some repeating itself, but when was creating the program, without this 2-1, sometimes the data is not set and it's skipped. So I quite really advise and recommend to keep this 2-1. This is kind of a wall that will protect when you can sending the data. That's all I wanted to share with you. This is coming from the experience of writing I2C in the STM32F1. Hope you enjoyed our channel, and thank you so much.